After a 5-year hiatus, we're very fortunate to have Professor Little back as one of our speakers. I think it was 2017. Uh, Professor Little, after graduate work in Southern California, Professor Little got a job at Greenfield Community College in 1969 and couldn't leave. He describes Western Massachusetts as the best place in the world to study geology. He discovered the rare Jurassic Age armored mud ball, which he hopes will become celebrated officially as the state of Massachusetts as a sedimentary rock structure. I can imagine that an armored mud ball fight goes very much different than a snowball fight, but I'm not going to sign up for that. So Professor Little is going to talk about the Magnificent Mysteries and Death, Geostories from Western Mass. Professor Little, it's great to have you back, and it's all yours.
All right.
Perfect.
Here we go. And obviously you're hearing me. So there's three things. There's Magnificence, Mysteries, and Death. That's what the talk is going to be about tonight. And if we were in person, I'd have a handout for you. If anybody would like the handout, please contact me by email and I will send it to you. But let's take a look at these three things. Magnificence, first of all, we have igneous, metamorphic, sedimentary rock types. We've got canyons, waterfalls, productive floodplains. And as a result, we have a really dramatic scenic setting, a lot of diversity. And then for mysteries, how did the Connecticut and the Deerfield rivers cut through that basalt lava ridge like the Holyoke Range and the Vocumtuck Range? And why are there 100+ foot deep holes in the Connecticut riverbed? Now, as fishermen, you guys know about those, right?
Sure.
And what are the true stories of the glacial potholes, and why does the lower Deerfield River flow north? Death. Why did the Pangea supercontinent have to die? Minerals and gravity can kill you too. And if it's wet, wild, and windy, go inside. You can die, perhaps quick, perhaps slow. And the answer to that is coming up. So welcome, stay awake. This program can save your life. But first, an important project I'm working on. It's about armored mud balls, saving these rare features. So the armored mud balls, in case you didn't know, is when hard mud falls into a stream, and this was happening back during the Jurassic time. The mud tumbles, gets round and sticky on the outside, and pebbles adhere to the rim, and that's the armor. And then you have to have quick burial, lithification, that means turning them to stone. And then 200 million years later, they have to be found. So that's the story of the armored mud balls in a nutshell here. But they're very, very rare features. And in fact, the ones that we have in the Connecticut River Valley are not only the most scenic ones, but they're probably the only ones, at least that you can easily see in the whole world. They've only been found in a few other places, and those other places are high up in mountains or along remote coastal cliffs, and they're just not very pretty either. They don't have a nice armor. Like if you look at the one in the lower right there, you see all sorts of nice quartzy pebbles that give it a nice definition. So we have the best, if not the only ones that you can see in the world. And the best place to see them is the GCC geology path, which is right at the south end of the building. And there's a guide sheet that you can find there. So I'm trying to make the armored mud balls a state symbol. See, there's 50 state symbols, over 50, including the corn muffin and the Boston cream donut. And I think armored mud balls are much more important and should be celebrated. Now, if you want to go to my website, you can learn a lot more about them and see many, many pictures too. And it's armoredmudballs.rocks. There's a petition you can sign up, and hopefully we'll have thousands of people and a great outcry to make these things a state sedimentary structure, as we call them. I also have a couple of books that I've written, and if you go to the website, you can learn more about those too. And now back to the show. And can anyone confirm that I'm still coming through okay?
Yep, we can hear you.
Oh, wonderful. So the sound level is okay?
Yes.
It's fine.
Okay, thank you very much for that. So back to the program. Let's take a look at Magnificence here. Well, we don't have a Grand Canyon or Rocky Mountains, but we do have the longest river in New England, and we have a number of 1,000-foot deep canyons and narrow valleys, scenic streams, waterfalls, and like I said earlier, those mysterious holes in the riverbed. We have a very wide valley in Massachusetts and Connecticut along the Connecticut River, meanders, pretty floodplains. And the thing that's really unusual about this wide Connecticut River Valley is that there is a central ridge line that goes all the way from Massachusetts here through Connecticut. And that gives us great scenic interest and some wonderful valley views. But how many valleys do you know of that have a long ridge line right down the middle? In this view from 1836 by Thomas Cole, can anyone see what the big difference compared to today's landscape? Did you notice that part right there? The neck of the meander is still there in 1836, but then in the spring freshet of that year, it eroded through and left us with the oxbow that I'm sure you all know about today. So why do we have all this magnificence? You know, it's due to geology. If we look at our geological heritage, our history, this is what has happened quickly. First, we had a collision of plates that gave us a supercontinent of Pangaea. And in the process, that did a lot of metamorphism. Oceans were squeezed up. We had igneous intrusions making granite. And so that's what happens when big plates on the Earth's crust collide. Eventually, Pangaea split. Over here, a rift valley, and that left us with sedimentary rocks, dinosaur fossils, of course, and a lava flow that we now see in the middle of the valley. And then we have erosion of the whole area, a regional erosional episode that created a flat landscape that we call the peneplain. And number 4, today, there's been uplift and erosion, actually over the last maybe 15 million years. There's been uplift and erosion to create the present landscape that we see with just a little bit of additions, and that addition would be glaciation. So the ice comes, the ice melts, Lake Hitchcock forms as the last glacier is melting, and then finally Lake Hitchcock drains about 14,000 years ago. The Connecticut River comes back to the valley, and that's what we have today. Very quickly here, still going at a warp speed here through geology. Do you know about the rock cycle? Do you know that there's only 3 types of rocks? The igneous ones, the ones that were once molten. Then we have sedimentary rocks, pieces, sand, gravel, mud that became rock from the erosion of all pre-existing rocks. And finally, we have metamorphic rocks due to heat and pressure. So this is what's really attractive about geology. You can get through your Geo 101 class and only have to remember 3 rock types. How about that? Okay, so in the Connecticut River Valley, we have all 3 rock types that are easily seen. This is why it's so great to study geology here. So we have a lava flow. In this case, we're looking south along the East Hampton, Northampton, Holyoke area. And we're looking along the line of the Holyoke Range, and that's the lava flow. We have dinosaur footprints in the sedimentary rocks. Sedimentary rocks surround that lava flow, and there's dinosaur footprints there. Oh, there we go. There's our dinosaur. Anyone chuckling back there? I can't really hear.
I'm giggling.
And then in the lowlands, there's landforms of river erosion deposition along the bed of Old Lake Hitchcock. Well, our valley here along the Connecticut Valley is kind of like a sandwich. When Pangaea split, we got this valley, this rift valley, and erosion from nearby mountains gave us a layer of sediment. That's the bottom layer of the sandwich. So sediment comes in, and then lava floods into the valley. That's the hamburger here. That's the hot part of the sandwich. And then after the lava, more sediments come in to give us other layers. So we have sediments on the bottom, a lava flow in the middle, and sediments on the top. Now, the next thing that happens to this sandwich is it tilts. And the sandwich tilts because we have a big fault as Pangaea continues to split. A major fault opens up on the east side of our valley. It's called the Eastern Border Fault, and that tilts all those layers. And then the next thing, we get erosion. Erosion wears away at all those layers. But here's a geological principle that everybody should remember. If there is a hard rock in the area, it will not erode very well, and it will stand up on the landscape. And so when we erode the sandwich, the top layers of sedimentary materials wear away, and that reveals the tilted lava. And that's what controls this ridge that goes up and down through Connecticut and into Massachusetts. Here's another view of a cross-section of our sandwich tilted with the lava in the middle. So when we take a look at these pictures of our valley, the sedimentary rocks, easy to erode, they form the lowlands, and the lava sticks up as the middle part of the valley. Now, please note that Mount Sugarloaf, which is shown in this view on the top left, Mount Sugarloaf is actually the layer of sedimentary rock that's underneath the lava. The lava is in North Sugarloaf, just in the view behind Mount Sugarloaf itself. So Mount Sugarloaf is sedimentary. And the geological map of Connecticut shows us this red line, and that is the tilted lava flow that you can trace all the way to New Haven. So quite a lava flow, right? To be on the same lava flow, now tilted, so you can follow that edge all the way to New Haven. And so we talked about lava. And if you take a closer look at lava, this is Titan's Piazza on the right. All those columns are due to the cooling cracks that form in lava, just like you see here in Iceland at this famous picture of a lava flow in Iceland that cooled, it cracked, and those columns are just due to the shrinkage cracks. They're not due to crystals or anything like that that's fancy. It's just due to the physical process of cooling and shrinking. And then the lava gets eroded, and the six-sided cracks prominently form the outcrop. Here in Greenfield, we see these columns. And this, once again, is the lava. It's tilted. Columns used to be straight up and down, but they got tilted by the faulting. And so just lava, cooled, cracked, and it's 200 million years old, and it's quite a beautiful sight. Okay, there's lava once again across our beautiful valley, talking about the magnificence and rocks. What happens if we go deeper? Let's take a look at deep metamorphic rocks. Now there's Mount Everest in the photo. And what would happen if we eroded 10 miles and saw what was underneath Mount Everest? What do you think? Lots of pressure down there, lots of metamorphism? Well, we can see that today. Pangaea was caused by the collision of plates. And those plates have since eroded and eroded for, roughly 400 million years. And so we have lost approximately 10 miles of overlying rock material. And that allows us to see deep into the middle of mountains. And as it tells you here, this is the Great Wall of Irving on Route 2. And look at this beautifully exposed metamorphic situation. So 400 million years ago, this was the middle of a huge mountain range, and now erosion has revealed it for us. And of course, the road building helps. There's lots of schist here with quartz intrusions. Let's take a closer look. So the schist is something you should know about schist and also slate. This used to be mud in the old ocean, the ocean before Pangaea. And then Pangaea forms, and that pressure creates the mountain and also the metamorphism, the squeezing created this rock. And if you take a look at it, it was the ocean before Pangaea. So the little graphic there on the right just shows you where North America was, and there was an ocean, and then New England crashes into North America actually to create these rocks. It's a rather complicated story, but suffice it to say that the ocean got squeezed up into North America, and the old mud becomes metamorphosed into schist. And so this is kind of interesting here, very interesting, because the schist is just filled with these veins of quartz. And where does the quartz come from? Well, guess what? Quartz is one of the first minerals to melt. So if you take a rock and you start to metamorphose it and you heat it up, the quartz that is included in that rock will change into a liquid before everything else does. And as I say here on the screen, it's like squeezing a chocolate chip cookie in your hand. It's the chocolate that becomes liquid. And so in this case, geologically, it's the quartz that becomes liquid. And there it is, all sorts of beautiful quartz veins. And they're called boudins, which is French for sausage. So there are all those quartz sausages. Now, when we're talking about metamorphic rocks, we can't forget gneiss. Here's Shelburne Falls, beautiful Shelburne Falls gneiss there, swirling bands. And the gneiss came from magma chambers that were underneath volcanoes, for the most part anyway. That's one of the ways you can get gneiss. So as plates are coming together, there's a process known as subduction, when the ocean crust goes down underneath the adjacent continental crust. And there's magma chambers down there that are feeding volcanoes. So when you get a collision and you push all those continental plates together, you're going to find that those magma chambers will be changed by heat and pressure. They'll be squeezed. They'll become a beautiful banded rock. And that's the story of gneiss. Old magma chambers now metamorphosed. I did want to tell you two more stories here. The stories of two schists, Goshen and the Holly schist. Now, these start out as mud in the ocean before Pangea. Now, everybody knows, I think, Goshen stone, beautiful schist, splits nicely, makes great stone walls and walkways. It's got black minerals in it like hornblende, lots of mica, that's the silver that's there as kind of a sheen across the rock, which is what makes it split nicely. You all know how mica has a flat cleavage plane, so it will split very nicely when you get a bunch of them all laid out together. Sometimes little garnets. And then let's compare this. Right nearby, there's the Holly schist. Now, the Holly schist is actually 50 million years older than the Goshen schist. So today they are right next to each other in adjoining towns, but they used to be much farther apart in time. But it was the squeezing that was caused by the collision of continents here, the plate collisions, that caused everything just to be all folded up, and these layers are now right next to each other, even though there's quite a time difference. But there's also a compositional difference. When you look at the Holly schist, the garnets are big. The hornblende, which is a iron-rich mineral, nice black mineral there, sometimes forming bow ties coming out from a common center. The iron-rich mineral has to have a source of iron, and that came from nearby volcanoes, which put volcanic ash and lavas into the old ocean sediments. So even though they're right next to each other geographically today, they are from different parts of the old ocean and 50 million years apart in age. So if you look across all of New England, we have all sorts of metamorphic rocks and a lot of schist, and that's from, once again, the old ocean before Pangea assembled. And I always think that's a fascinating story, from the slate on your roof to the beautiful rocks that you find in Goshen and other places, perhaps in yours, is from the ocean mud before Pangea. So once again, we're looking at Magnificence, and these are magnificent rocks with an amazing geologic history. So I'm going to skip past rocks now, but I should note that, boy, we have dinosaur footprint fossils here. Those are wonderful. Those are magnificent. And of course, we have the rare armored mud balls, and I'm excited about those. So schist rocks, but we have some other good ones here too. And now let's take a look at mysteries. So we'll look at holes in the rocks and riverbeds and the landscape. We'll take a look at why the Connecticut River cut through the Holyoke Range and also the Deerfield River through the Pocumtuck Range. And why did Pangea have to die? Well, let's start there. The Connecticut River drainage system is in this particular location because Pangea split. And that's what caused the old Rift Valley. And that's a very good thing, because without Pangea splitting, we wouldn't be here in this region tonight. We would be in a landscape that would be like the hills of northern New England. It would be isolated, up and down hills, the lowlands, forest covered, not so interesting. We would not be along a major valley. So thanks to Pangea, thank you, thanks to plate tectonics, that's why we're here in the remains of the old Rift Valley. But why did Pangea have to split? Why did it have to die? Well, let's take a look at the Earth. Why did Pangea have to die? Deep in the Earth, it's really hot. And that heat has to come out of the Earth. It's always coming out of the Earth. But when you put all the continents together in one space, then the land underneath is going to start to expand, because that heat can't get out easily. And so if you can imagine, you put all those continents together and then have the middle expand because the heat can't get out, pretty soon those surrounding continents are going to slide off that bulge there, that expanded bulge. And so all supercontinents have this problem. They can't just stay there. They're going to break in the middle and drift away again. So heat builds up, expansion, continental split. And that's why we're here. Well, the topic now is holes. So I'm going to tell you the whole story. Chuckle, chuckle, chuckle about that one. The whole story. It's coming up if we're lucky. So first of all, the potholes. I think you all know about the potholes. And it's a beautiful spot up there. And they're called glacial potholes. Now, are they glacial? There's also something called a plunge pool. So these potholes, or are they plunge pools? Or as you're going to see, they're both. And the Shelburne Falls have the world's largest, like they say. And how long did they form the potholes? So as it turns out, they are not glacial, not even glacial meltwater. And if we look at potholes versus plunge pools, in a pothole, the river flow will cause twirling stones. So they will drill downward, and you will be left with a hole, just like a drill hole, that has a level rim around the outside. So it's a drill. Now, if you have a plunge pool, that's a waterfall. So water will actually fall and create a plunge pool at the base of the waterfall. So the rim of the waterfall is above the exit point of the hole. It's like a jackhammer as opposed to a drill. So we have both of these things in Shelburne Falls at the pothole area. And what they are calling the largest pothole, which is over 30 feet deep, it's actually a plunge pool there, because there's an obvious waterfall where there's a lip and then a lower point where the water exits. And how long did it take to form potholes? This is really an interesting question, which is very nicely answered, by the way, because the potholes have this history. They're graded to Lake Hitchcock, and therefore, or there was a covering, as I'm going to tell you here. There was a glacial gravel cover that was graded to Lake Hitchcock. So the potholes were not even formed. They couldn't start forming until Lake Hitchcock drained, and that was 14,000 years ago. And so you're going to find that these beautiful potholes have been formed in only 14,000 years. And I'm not sure about you folks, but that seems like a fast erosional episode. But that's what happens when you put water, rocks together that are twirling around. So to take a closer look at this, go back to the glacial age. There's the ice melting back. As the glacier ice melts back in this area, kind of hemmed in by the surrounding hills as the glacier is getting thinner and thinner, the outwash meltwater streams will send lots of gravel into the surrounding valley. And it actually fills, to a large degree, the valley of Shelburne Falls and Buckland here. It just covers these areas. So I'm going to blank the screen out here. So this is all cover. It's all fill. Outwash sediment covers the landscape. And now these gravels are graded down to Lake Hitchcock because the river's flowing towards Lake Hitchcock. And so Lake Hitchcock did not cover Shelburne Falls, but the river, the Deerfield River, flowed to Lake Hitchcock. So it was on that gradational plane. So 14,000 years ago, Lake Hitchcock drains. The Deerfield now can downcut. Once the water of Lake Hitchcock is not there, the Deerfield can downcut. And when it does that, it finds itself on top of that bedrock of the present day potholes. And in the process, it creates the potholes, and it also creates plunge pools where the water will, as I said earlier, just plunge, dropping down by gravity, and there'll be a plunge pool at the base. So when you look at the pothole area, some of those potholes are actually plunge pools because there's a plunge. And others have a nice circular rim, and those are the true potholes. So I hope I've cleared up some of the questions that you might have about these holy rocks up there in Shelburne Falls. Now, where's the biggest pothole? Well, an internet research discovers that 40 to 50 feet wide here in Finland, there's a giant pothole. If you take a look at this one, it does have a level rim. So it is not a plunge pool. Okay, another whole mystery. There's holes on the Montague Plain, like Lake Pleasant, Green Pond, and a few others that are nearby. Now, I think most people know that the glacier was here. Ice blocks can become separated from the glacier and covered by surrounding gravels and other deposits. And that, when they finally melt out, that will leave a hole. And so when you take a look at places like Green Pond and Lake Pleasant, it's about 70 feet down from the surface of the Montague Plain down to the water level here. And the water flow into these lakes is totally by groundwater. There's no stream flowing in of any consequence anyway. So it's all seepage from the porous surroundings of a huge delta. The Montague Plain is a huge delta into Lake Hitchcock. And now some really strange holes here are these 100-foot deep holes in the Connecticut riverbed. And these are so fascinating because unlike this graphic, as you go over the along the Connecticut River, you go over the hole, and because of the water level, you don't know that the hole is there. Am I right? So they're kind of mysterious, aren't they? Thanks to sonar depth fish finders here, we can figure out where the holes are and how deep they are. Okay, how did they get there though? How do you get a hole in the riverbed? Well, the answer to this is actually not well known, but I think I can make a really good case of how those holes got there. And we see nearby holes. If you take a look at this graphic, there's Turner's Falls, there's a ridge called the Lily Pond Barrier. I think the next picture, another picture is coming up that will show this. But here's the story. Back when Lake Hitchcock was here, there were deposits all across the valley, just like up in Shelburne Falls. There were deposits all across the valley. And then when Lake Hitchcock drains, the rivers come back to the valley and they find, they start cutting down through that cover of sediment. And in this particular case, there's a bedrock ridge that's buried under the sediment. And that's where a waterfall develops. And there's a plunge pool at the base of the waterfall. Okay, so where is this today? It's right here. So there's a waterfall. This is Barton Cove, as you can see. I think many of you people, I'm sure, have been here. Camp area there, nice picnic area and so forth. So here's the Lily, it's called the Lily Pond Barrier. And the river initially fell over the edge of that, what used to be a buried ridge. So there's a waterfall there, and they're now abandoned. And there's another one there. And there's a third one right there. Now through this bedrock obstruction. And the Connecticut River, once that was breached, was able to work its way back upstream, cutting and cutting and cutting, but it left the hole behind. So today, if you go down to any of those holes, you'll see that they are tens of feet deep. And if you go to the one that's right there at the narrow, so-called narrow, if you can see my pointer, that's over 100 feet deep right there. So it's quite impressive, nice hole. And as you take your boat through there, it'll go from about, what, 20 feet. And then all of a sudden it will drop down to over 100 feet and it'll go back to 20 feet in just a couple of seconds. So it's just an amazingly deep hole. And that's a plunge pool. Now, once the Lily Pond barrier was breached, the river was able to cut downward and back to another obstruction. So notice how narrow the valley is right through this area here. That is a ridge line, sedimentary rock that was all across the valley. The river encountered that, another waterfall, another deep hole. Once that ridge was eroded through, it went back to the next one, and there was another waterfall, another deep hole. And this kept going on and on and on until you reach the French King Bridge. Now, today we see the French King Bridge as you see here, picture on the left. But you can imagine that as the river is cutting its way back through the bedrock, because the rock on the right side of the French King Gorge was once connected to the rock on the left side of the French King. But the river flowing through there had to cut its way, leaving that steep-sided valley in its wake. So in other words, it did this by waterfalls and rapids. So if you want to be extreme about this, you can imagine a waterfall like you see in that picture doctored to the right, a waterfall eroding its way through the French King Gorge. And don't you wish we had a time machine to actually see that? So how long did this take? Well, we know that with Indian artifacts down in the riverside area of Gill, that there were Indians there around 9,000 years ago. So the waterfall was probably there around 9,000. Lake Hitchcock drained about 14,000. So somewhere between 9 and 14,000, all this was happening. Boy, once again, wish we had a time machine to see it, but that's the evidence on the landscape. Another river mystery is why the Deerfield goes north up to Greenfield as opposed to going past Mount Sugarloaf. So it's kind of weird too, because when the Deerfield goes north, the major trunk stream here is the Connecticut, of course, and that flows south. So it's very rare to have a tributary stream flow in the opposite direction of the trunk stream. And speaking of streams, I'm a little dry, so I'm going to have a sip. Pardon me just a second. Okay, so back to the program. This is, if you see the red arrow, that is the direction that the Deerfield should have gone, right? It comes through the hills of the Berkshires there. It should have kept going to the south, the southeast, and it should have joined the Connecticut River down there by Mount Sugarloaf, not going up to Greenfield. Okay, so here's the story. When you see weird things on the landscape, blame the glacier is my suggestion. So in this case, when you have a glacier, it depresses the land just by the weight of the ice. And when the ice melts away, the land rebounds, glacial rebound. And so when Lake Hitchcock was here, it eventually drained, of course, and the land was in the process of rebounding. So in the process of rebounding, there was apparently a slight tilt to the north due to this post-glacial rebound. And that caused the river to flow that way for a while anyway, or get started going that way. See, once a river gets started in a certain way, it's hard to reverse it. Now, if you know something about rebound, you'll know that the northerly areas eventually rebounded more than the southerly areas. But if you're looking at the development of post-glacial rebound, it's kind of a roller coaster effect where the southerly areas start to rebound before the northerly areas. So even though the northerly areas end up going higher for a while, there can be a slight tilt to the north, which then reverses. Boy, how many people get confused by that statement? Okay, ask questions later. But this is really cool too, because the Deerfield went north, but few people realize this. The Connecticut River actually went into Greenfield for a time. So it swung over there by GCC. It left some old oxbows behind. You can see those meander scars out on the meadows. And then, of course, fairly quickly, the rivers reorganized to the way we see them today. So the final mystery of this program, how did the Connecticut River cut through the Holyoke Range? Well, if we go back to our overview of the range here, here's a painting by Will Sillen. If we take a look at this, there's the Holyoke Range from this vantage point and the oxbow, of course. if we go back through geological time, we go back to the end of the age of dinosaurs, the old mountains of the Rift Valley and the collisional event that made Pangea, those old mountains are now eroded away. It's a regional flat surface, which we call the peneplain. And so I'll put that line there. That's where the old peneplain used to be. So all the flat surrounding hillsides, if you look way off in the distance, it's all flat up there in Vermont and central Massachusetts and so forth. And that's the remnant of that flat erosional surface. Well, the tilted lava of the Holyoke range was part of that old peneplain surface. It was all part of that. And so now let's bring a river back into this situation, into this story. So due to the rainfall, of course, there's going to be rivers. There was a river that was flowing across the peneplain surface. It would have been on top of this buried basalt bedrock, what we now see as a ridge, but was then part of the old peneplain surface. Now, given time, there's uplift and then down cutting. So when you get the down cutting, you're going to produce this valley through the ridge, and it creates something called a water gap. Now, here's the series of diagrams that shows you top left, there's the peneplain, and then 2, we have the uplift and the stream starts to down cut. And then 3, there's what we call differential erosion. The weak layers erode away, become lowlands, and the river finds itself through the ridge, flowing through the ridge because it started out on top of the ridge. So that's the water gap mystery. You need a peneplain, you need uplift, and then the river down cutting through the hard rock, and then generally erosion of the softer surrounding rocks creates the landscape that we see. Well, are you all waiting for death? Here we are. The final topic today, very appropriately, I guess. Yes, save death for last. That's a good advice for everybody. So death by rocks. Here we go. Death by rocks. What is in rocks? This is perhaps the most important thing that you don't know about coming up next here. We have minerals in rocks. Rocks are made up of minerals, and sometimes you can have arsenic in them, and sometimes you can have uranium that degrades. Here's the decay series, and it can become a gas called radon. So let's take a look at arsenic and uranium in your well water, first of all. As the caption here tells you, U.S. Geological Survey researchers analyzed water samples from a lot of bedrock wells in Massachusetts. They found that 13% exceeded federal drinking water standards for arsenic, and 3% exceeded standards for uranium. So the probability that an individual well poses an immediate health concern is low, however, but it is prudent for private well owners to have their wells tested, and hopefully you can do that. Now, this is kind of funny here, pardon my joke, you're in luck, because the results of urine analysis indicated that no one in the study area had arsenic or uranium in their urine at levels of health concerns. But anyway, if I were you, I'd get my water tested anyway. So here's a map that shows you where the levels of concern are. And there's not too much over here in our area of the state. There's a lot more in the eastern central part of the state. Okay, but let's take a look at radon. Now, smoking, as I'm sure all know, is the #1 cause of lung cancer. But guess what is #2? I won't take you too much to guess radon, I guess. But yeah, that's it. It's radon. So what is radon? A colorless, odorless, tasteless, and radioactive gas that originates from uranium's radioactive decay. It's present outdoors at low levels, but this is the problem. It can get trapped in your house, and particularly it can come in through your water supply. It can come in through cracks in your foundation. So the rule here is everybody needs to get their houses tested. I'm going to tell you more about that in a second. So radon is estimated to cause tens of thousands of lung cancer deaths each year. So only smoking causes more. So if you smoke and your home has high radon, your risk is even higher. And so radon is the greatest geological hazard. How many people knew that? Well, how does radon get into your home? The graphic on the left is kind of weird, but that's supposed to be a vacuum cleaner. Your home actually kind of acts like a vacuum where the air is sucked into your home. So this is what happens. So radon is found in homes, new or old. It could be with a basement or without a basement. It could be on ledge, or your house could be built on sand. Lots of diversity. Radon can enter a home from the ground, cracks and foundation from your well water. So particularly if you have well water, that's the greater source of radon exposure. So you should test your home. I'll tell you how to do this. There's a handout page, which you of course don't have tonight, but I'm going to tell you how to get it, and you can get a free radon test kit. So have your pens and pencils ready, everybody, or email me if you don't get this. First of all, how does radon get into your house? Well, your house protects you from the wind. And if you take a look at the wind tunnel effect here of your house with wind blowing against it, there's high pressure on one side and lower pressure on the other side of your house downwind. That will tend to create an effect that will suck air from the ground into your house. There's a low pressure zone in your house, and it will suck gases from the ground into your house. So how are you going to mitigate this? Well, one way to do this is they change the air pressure. So they will install blowers for one thing, and they'll push air into your house, and that will push the polluted air out of your house. That's one way to do it anyway. So there is a Massachusetts radon office, and actually it's located in Northampton, so it's not too far away. And if you call the radon hotline, you can get a free test kit, at least you used to. So that's 586-7525. So how about that? I called this a while ago. I got my test kits. I think I got 2 of them. And you test the upstairs air and the downstairs air. And of course, the worst thing is if you're living in a basement apartment or bedroom, spending a lot of time surrounded by your foundation walls, that could be the worst. Anyway, get tested. If you buy them online, they're usually under $30, but you should do this. Another death by rocks this time. Well, what about mining? Is it pretty obvious that if you're working in a mine, you are going to be at risk, right? So as it tells you here along the right-hand side, the mine may be gone, but the holes, disturbed land, and broken rock dumps remain. The rain falls. And even if you're not working underground, you can still be affected by mining. There's a lot of surface area for weathering. Sulfur, which is a common thing that's in mining areas, goes into solution and you get sulfuric acid. So it's called acid mine drainage. Now everybody knows pyrite, I think. Fool's gold, iron pyrite, it's iron and sulfur. So this very pretty mineral can dissolve away and get into your groundwater and perhaps into your well water, and it can leach out onto the ground. And let's take a look at one example of this. The Davis mine up right along the border of Roe and Heath. Well, the Davis mine was active up into the early part of the 1900s. And anyway, there were collapses due to, as they say, poor mining practices. And by 1937, there was just a blacksmith shop and about 150 cellar holes. So it was an iron pyrite mine. And it wasn't the iron they were after the sulfur. A lot of people don't realize that. So here are some of the remains of this mining area. There are 4 shafts that are capped, and one is 1,800 feet deep. The average sulfur content was reported to be 47%, copper 1.5%. So it's hard to believe that these structures were up there in the hills of Roe, isn't it? I mean, look at that. That's not there anymore. Same with this. Here's in about 1909. So what's it like today? Well, Death to Organisms is the title here. Here's leachates coming out of the mining dumps. And as it comes out, UMass studied this area and found, take a look at this, that for 5 kilometers downstream, so that's about, what, 2 miles downstream, no macrobiotic organisms, no fish, no salamanders, no other large organisms. And so that's a picture of what this drainage area looks like on the right. Okay, another hole. You see the light at the end of the tunnel there? Let's take a look at another hole. So this is the Hoosick Tunnel. So it is claimed that 195 people died in or around the tunnel over the 20 plus years of construction. It was the so-called bloody pit. But what's in those mountains to make it so dangerous? Well, let's take a quick look at this. When we have the collision of plates, do you remember how there was metamorphism and the great squeezing that we saw there along Route 2 that gave us the quartz veins, the boudins, the sausages of quartz? Well, here's a geological map of, this one's from Vermont, but it shows you exactly what's happening in a map format. This was the edge of the North American continent about 500 million years ago. And there's a lot of limestone that was in that warm, shallow sea. The limestone is now this metamorphic rock that we find in Western New England, marble, and it's soluble. Marble is soluble, weak to the forces of weathering. So if we take a look at that old ocean and the marble that came in it, it got squeezed up by the collision of continents. And this is what it looks like today. This is the geological map. And everything is just swirling, swirling, swirling up and down and around, faulted, bent, folded. Now, if you look at trying to put a tunnel through these rocks, you have explosions, falling rocks, and floods. Floods, yes, there's floods. Imagine digging a 5-mile tunnel, the Hoosick Tunnel, through these rocks with weak, saturated, old limestone, now marble zones, soluble rock zones. So imagine that. There's your 5-mile tunnel through this really complicated rock structure. Now, marble is soluble, weak to the forces of weathering and erosion. And some of the surface exposures that show this is the Catamount Caves up in Coleraine. And there's places where you can see these marble areas dissolved away for the most part. Other places, well, there's marble quarries, of course, that's not natural. That's not a natural hole. But if you look at the Natural Bridge State Park in North Adams, that's where there is actual solution there with caves surrounding in the area. So the weak marble zones, here's an ancient picture, historic picture of the Hoosick Tunnel. And as they were mining out the Hoosick Tunnel, they encountered these marble zones, and it was called porridge rock. All of a sudden, water would flood in. And imagine working underground, explosions, weak rock, and then sudden water coming out at you. And of course, that's death. Now, the photos I put here, as it says, these are not Hoosick Tunnel, but it illustrates the process. Now, the tilt of rock layers can kill you too. It's steep slopes, rainfall. Let's take a look at Hurricane Irene back in 2011. Back here in the Mohawk State Forest, there's some very steep slopes, and the rainfall that came down those steep slopes, and the tilt of the rock layers are right down into the valley. And you can see here where the arrow is pointing, these layers are very slippery. They've got a lot of mica in them, and they just don't allow the soil to stay there for very long. So there were slides, these debris slides that just came right down the 1,000 feet of the slope onto the road. Now the black car here, as it says here, this guy got caught between 2 slides at about 11 p.m. on August 27th, 2011, almost got pushed into the flooding cold river at this point, right up over the guardrail. Look at that. Talk about getting close to death. The gray car came in later, but wow, that was close. That must have been pretty scary. So anyway, you have the original position of the soil on top of tilted rock. And when that comes down, boom, goodbye. So what you want to do is build your house on some good flat lying rock. because that's much more stable than being on a tilt. But then again, as it says, being on an overhang is kind of tempting fate. Okay, one more. Dangerous geological hazard is flash floods. Are you safer living by the mighty Connecticut or by a scenic bubbling brook? Got your answer? Okay. It's going to be the brook. That's more dangerous, safer by the big river. Now, this was a small rainfall event back when I did this slideshow last November. Put this together here. Here's the Connecticut River. It rose up at a slope like you see here, nice little curve up, then it goes back down again over the course of about a day. Now, here's the lower Deerfield River at Stillwater Bridge. So there's the water, and then all of a sudden, boom, up it goes in just an hour or so, and then it filters out away. So these are called flashy streams because they tend to flash flood. They have a shorter drainage area, and the water just drains off very quickly. This was the Green River in Coleraine. And you can just see, boom, there it goes, very fast. Now, let's take a look at Hurricane Irene, and we'll look at the Deerfield River, which is a pretty big river. And in about, as it says here, 20 feet in 2.5 hours. So there was so much rain coming down the Deerfield River that it just bumped that water level up 20 feet in such a short time. Boy, that is a flood. That's a flash flood. Various pictures are shown on your screen now of flash floods and all those events of erosion that happened from them. The one that you're seeing now, Big Thompson Canyon, Colorado, 1976, almost 140 people killed in homes and campgrounds. 4 hours of heavy rain did this. So watch out for flash floods along small streams. So does the Connecticut River have flash floods? Well, we already talked about the Deerfield River. Boom, that's a definite yes. Here's the Deerfield at Shelburne Falls in normal times, and there it is during Hurricane Irene. What a great picture this was. And there's the quilt shop, or the studio. There used to be, as the picture on the right shows you, it used to be where the arrow is, and then it went down to where the second arrow is. So in conclusion here, is this your dream house? Nice little house by the bubbling brook. Well, watch out for radon. Watch out for flash floods. Watch out for steep hillsides with tilted beds that can give you a landslide into your back door. So if your house is in this location, do some remediation. There's two things I'm going to suggest. Do some remediation or plant this in your yard. So civilization exists by geological consent. Have you heard this quote before? Subject to change without notice. A man by the name of Will Durant. And I've heard about Will for a long, many years because of this famous quote. And only recently did I realize that Will Durant is from North Adams, born in North Adams anyway. And anyway, he's quite a famous person, philosopher, historian, writer. So the Connecticut River Valley region is a really interesting place, of course. It's the best place in the world to study geology. And let's save the rare armored mud balls, everybody. And what has been seen cannot be unseen. And that's the end of my program. And if we can consult with each other, I'll be glad to answer questions.
Thanks a lot, Rich.
The western portal, the Hoosick Tunnel, I guess it's probably 3 years ago now.
Yes, well, I didn't hear a
Was
question.
The collapse on the western portal, the Hoosick Tunnel, was that a result of porridge rock?
You know, I'm kind of missing part of the question, but it's about the collapse of the western portal. And I can't tell you exactly why that collapsed. Are we talking something recent or historic?
This was about 3 years ago. It was in February. It was the last year we had the last year we had the Flies, Pies, and Lies. So that would have been 2019,
well,
maybe.
Okay, I'm not familiar with that. So I'm just.
I wish that
why.
one of our members, Mike Hayden, was here, because Mike Hayden was, he's like a trained fiat, He's into trains. You know, he's the kid he's the guy who will run out and wave and ask them to blow the horn for him. You know, but apparently when they constructed the tunnel, the first mile in on the western side is all brick because they had trouble with it collapsing. They weren't into solid rock. And apparently that has something to do with the reason why they had to build that as brick or stone as an arch inside there to prevent that. And then after 150 years now, it finally gave through.
Okay, well, there may be some other reasons behind this, like the structure of the brick, but when you get over to North Adams, you're in the marble belt. When you're over in Florida, you're not so much in the marble belt. You know, there's a lot more of the marble over on the other side of the mountain.
Okay, so it wouldn't have been
There.
as probably would have been stable on the
side.
western
So,
side. Yes. Okay, good.
Yes.
Yeah.
Mike Vito, did you want to say anything about the Davis mine? That was an area that came up. I was
Yeah,
surprised to see it come up in the presentation.
I know, right? Uh, just so you know, Doctor, we had taken a look at the UMass project over at Davis Mine Creek. I guess they've been studying the area, looking at the effects of the Davis mine. I guess the mine shut down in 1911, and they used to make, this is going to shock some people, sulfuric acid right there on site from the pyrite. And a lot of the pyrite still seeps into some of the groundwater that comes up into the brook. But what intrigued myself and some folks at the U.S. Geological Survey over at the Conti laboratory was that the folks at UMass had discovered possibly some type of organism that was eating up the acidity in the creek. So year by year, well, in this case, probably tens of years, it's getting a little bit less acidic due to some natural organism that exists there. Do you know anything about that?
Your statement is kind of broken up, but I think I get the gist of it. And actually, I read about the UMass work, but I do not know what you're talking about in terms of specifics.
Yeah, okay. We were looking at that as if this organism worked as maybe working with UMass, and whenever they were ready to see if we could restore the native brook trout to the brook. It'd be a nice project for us, but there's too many questions still, so leave it at that. But
Okay.
great presentation. Thank you.
Okay, thank you, everybody.
Any other questions for Dr. Little? Thank you very much, Dr. Little. That was very informative and just fascinating stuff. And it's great. There's so many aspects of it. We have a recording of this Zoom call, so we'll be able to edit out that little section where you had some technicalities, as we like to say, and we'll put that on our website. And I certainly am gonna review it because it was a lot of information in a very short period of time. But thank you, and I hope members of our chapter will actually participate in your armored mud ball campaign.
Yes.
Sounds like a good one.
Yeah, and actually that is very, very effective. If people have any groups that you're associated with and you want to send out just that www.armoredmudball.rock.
Excellent. We'll put that up
The
when we
whole
put the
project is just laid out very quickly there. And, you know, it takes a lot of people to convince legislators that something like this is important to save and celebrate. And we have it. Nobody else in the world does. We need to be very active and, you know, try to pat ourselves on the back here for recognizing this. And it's unique. Thanks for your help.
Thank you.